Hello, everyone. I want to talk today about doing analysis using a Monte Carlo process. I'm going to be using SIPmath for that Monte Carlo. And for the evaluation and analysis, we're going to be using this fishing problem. And this is not fishing with for fish with the fly rod and the fly. This is fishing in the sense of oil and gas, where I'm going down in a well. So we're not going to be doing much modeling. I'll show you a model, but we're not going to be talking about too much about the model. We're going to be just talking about the analysis. So the objectives here is, as I said, using Monte Carlo with SIPmath to evaluate multiple decision policies. And I'll describe further what I mean by a decision policy. We're going to use graphics to describe and summarize results in tables. And we're going to find out that different value measures can result in different decision policies, but very similar results. And then we might be able to identify alternative solutions that make business sense, but not identify with maximizing any of the value measures that the decision executive might have identified. So what is the fishing problem? So we have a base business production. We'd like to remove a packer from a production well in order to produce from a deeper zone. However, this fishing operation is not succeeded after several days, and similar fishing jobs have historically had a 60% success rate. The unit seeks to determine what to do about this and has held a DA framing session to brainstorm the issues and alternatives. So what are some of those alternatives? Well, we can continue fishing operation and, if successful, produce from the deeper zone. Okay, that's what they have been doing. They could drill a sidetrack well to a deeper zone. Sidetracks typically have an 85% success rate. Or they could just drill a whole new replacement well to the deeper zone. Or they could say, forget it, let's just plug and abandon, no further action. And we can do any combination of the above alternatives if we want to, depending upon the success of the fishing, the sidetracking, or the replacement well. The primary decisions identified were value creation, and that is measured by a profitability index of 0.4. Profitability index is, you can look that up on Wikipedia, but it's basically net present value divided by the capital. And there's different ways of defining the capital. In this case, we're going to use a discounted capital, because oftentimes these things have capital that's spread over many, many years. And you don't just want to add them up. You want to take a discount, so you've got discounted value over discounted value. Okay. So if you take all those, what I've described as the problem, and put it into a tree, and this is just for graphical purposes, you can see that we have to make a decision whether to fish or not. And then we have to make a decision how long to fish. And then we get the uncertainty of the fish success. And then we have to decide, do we going to sidetrack now or not? Obviously, if we're not successful, then we can decide to sidetrack. But that could be no as well. Or we could say yes. And then there's a cost for the sidetrack. And no, then we could come over here and drill a replacement well. Here's the success of the dry sidetrack. And then you got the replacement well cost. And then you got all this other stuff over here that adds on to this. I think there's like 4 decision variables, 1, 2, 3, 4, and 8 different uncertainties in here. So it's a lot of stuff to run, and you got to build a model for that. And we built a model for it, and we ran the thing in the decision tree, kind of as shown here. And that was okay. That gives you an answer. And you might say, okay, that is the answer. And then you got to figure out the decision policy, because what happens is you get an answer back out here, and it tells you this first one, but doesn't necessarily tell you all this other stuff. And so there are ways to do that as well, but it's a little bit complicated. It doesn't really facilitate doing a complete analysis of all the other alternatives. And we'll see how that comes into play here as we go through this. So the management questions we're trying to ask is, given the frame of the problem, what's the best decision policy? And we'll abbreviate that DP. Show the alternatives in an investment efficiency chart and discuss fishing or not fishing, just replacing the well, P&A. This investment efficiency chart is really the NPV here on the y-axis and the capital on the x-axis. Actually, it's the discounted capital, what I use. And then discuss the incremental value of fishing for 1, 2, or 3 days, 10 days, or the sidetracking and or the replacement well. And then they wanted to know how often do we replace the well. Okay, so let's flip over to this model. So here's the model, and we're not going to go through this whole model, but I just want to say that there is a model, and all the uncertainties and decisions are defined here. And it comes down, you got the inputs by time series. So we've got here, this is from 24 to 37 years, and so forth and so on. We got some graphics down here. That's all great. But what I really want to talk about is the analysis. How are we going to do this analysis? Well, we're going to do the analysis by coming over here to this decision policy. And what we're going to do is define all of the key decisions that we need to make. And what do we need to make for decisions? We need to make, let me blow this up a little bit. We need to make decisions on the number of days to fish. So there's 1 day of fishing, 5 days, or 10 days of fishing. We can fish or not fish. We can sidetrack, and we can replace the well, yes or no. And so this represents all the different combinations here. And then we have a reference case. And this is using experimental design in SIPmath. This can be done using VB, and Crystal Ball are at risk as well. But the idea is to be able to lay out all these different alternatives and be able to run them all as one shot. You don't have to run multiple Monte Carlos. That's all run for you automatically. Okay? And so when you do that, you can then take these results, and here I've captured things like NPV, the value creation. Value creation is the NPV above the criteria. In this case, we're using a 0.4 criteria. We've got the discounted capital value, discounted value of investment. We've got the profitability index, and we've got the chance that we drill a replacement well. Okay, and so we got all these different alternatives, and then we can come down here and plot all of those on this capital efficiency chart. And we see here, these are all these different scenarios going from 1 to 16, right? And so from 1 all the way up to here is 16. Well, there's no reason we would do these really, because the NPV is so much smaller than these over here, and we're for very little more capital. So what we're going to do is let's focus on just these up here. So I've kind of expanded that chart or zoomed in on the chart. And here we can see those that are highest. And so the ones we really should be looking at are 16, 12, 8, and 4. 16, 12, 8, and 4. So where's 2? Oh, here's 2 way out here. So why should we consider 2? Because there may be different value measures that people have. Like, let's just get on with it. Just go ahead and replace the well. We've got maybe we have a rig there that can just drill that well. We don't have to involve a lot of manpower in looking at all these sidetracks and the fishing operations, because they may be useful elsewhere in my portfolio. So this really becomes a portfolio problem as well. So that's one alternative that looked pretty good. And here's the NPV. We could sidetrack and replace, but not fish. That was another one that was there. The maximum NPV is we do everything for 1 day. We can maximize value creation. So we do everything, but we do it for 5 days. Interesting. All right. Then there's the maximum PI, profitability index, which we do everything but replace the well. And then I've highlighted one more over here that we can talk about. Oh, one more point. The other thing we should look at is the uncertainty, because these are all expected values. So if I come down here and plot all of those points that I just talked about over here, and the distribution of NPV, we see that all of them look almost identical, other than this one blue one, which is policy 15. And 15 is this one that does not replace the well. As a consequence, it has this big downside here that we may wish to get rid of, unless it's got some other qualities that make it really attractive. Okay, let's flip over to a summary of these highlighted strategies. And here they are. The question to ask is, typically I would use the maximum value creation as my decision criteria. That's my personal decision criteria. And I can see that I spent $239,000 discounted on capital to get 2677, which is only slightly less than the maximum NPV. And I saved quite a bit in capital. I could maximize PI, but that really drops down my NPV. That makes no sense to me at all, even though some people might argue, well, that's the way you rank your projects, is by PI. Well, not in this particular case. I'm going to reject this get on with it because I think we have sufficient resources. We can always back up to that if I get up to higher level management and they say, no, 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 everything else you're saying, Brian, doesn't work. But the case I really want to look at is over here, this case 16. Because now let's compare that to this value creation case. I lose about, what, 40? 40 in NPV. But look at the change in capital. My capital versus the value creation is 40 plus 25, right? Lower. So I save a lot of capital. And that's strange between comparing this one to this one, because they look identical, except this is actually drilling longer. This is doing fishing for longer. So why does a fishing longer actually have a reduced capital? Well, to do that, we need to go look at the model. So we go back here to the model and back up here someplace. Fishing days. Days required to complete the drilling, 1, 5, or 10. Chance of success, 15, 40, or 60. So by drilling an extra 5 days, I increase my probability. I have a 50% increase in my probability of being successful. So that's what's dropping my capital over here on this chart. The 176. 6.3% chance of drilling a replacement well versus 9. Now, as you look at this slide, you may come up with a different answer. Now, I'm not saying that my answer is right, but if I was the decision maker here at this point, I think I would go with 16, as long as I've got the resources to expend on the fishing and the sidetrack and the replacement well if necessary. What have we learned by doing this? We want to structure the model to be consistent with how we want to analyze the opportunity. In this case, we want to be able to run all the different strategies. By the way, the method I'm talking about here works really well with value of information, because effectively that's what we're doing here. We got information. If I come back here to this becomes information. It actually becomes perfect information that I can then use for the sidetrack. And then I get, I don't know whether this is sidetrack success, is perfect information for replacing the well. So, and obviously the fish, yeah, we already talked about fishing. So this is really a value of information, but it's perfect information, but we still need to figure out the decision policy. We use selected graphs that are most easily understood by the audience. You do not want to spend all your time trying to explain some innovative graphic that you designed. Use things that they're used to seeing. You don't have to spend time explaining it to them. They immediately understand what the axes are and how to read them. This capital efficiency chart of NPV versus the present value of the investment easily compares the EVs of the different alternatives. And we saw that on the chart. And the Monte Carlo approach can simplify evaluation with multiple alternatives and clearly identifies the decision policies. So I hope you find this useful. This applies whether you're talking about an individual project or you're talking about a portfolio. It can also be used on very large projects, or in this particular case, it's a pretty small investment, just one well. So consider using this as you do your analysis. Thank you for watching.